Hello everyone, Mission Nostalgia once again, and welcome to a new series of videos called Talking Hardware. So in every video of this series I am going to gather as much information as possible regarding the hardware of a particular console and share it with you guys. This is something that I always wanted to do because, except for the fact that I enjoyed playing with these consoles as a kid, I was also interested to find out how they actually operate. Now I know that this may sound a bit intimidating to some of you, especially those who want to find out what's really happening inside those little devils but do not have the technical background. Well, fear not, as I'm going to do as much explaining as possible when it comes to technical stuff, so that you can also follow along. Of course, if you have any questions, please feel free to ask them down in the comments and I will do my best to answer them. I'm warning you guys that it's going to be quite a lot of information, so get ready, grab a cold one and let's dive into the magical world of hardware. And what a better way to start this series than to get a closer look to one of the most beloved handheld consoles, Nintendo's Game Boy. Now, of course, the Game Boy was the undisputed king of the handheld consoles back in the late 80s and 90s, since it outsold all its rivals. However, in terms of hardware, it has a reputation for being outdated, even for 1989 when it was released. But is that actually true? Spoiler alert, it is. By the way, if you want to find out more about the history of the Game Boy, you can find my video down in the description. So enough talking, we have work to do, I have a screwdriver and I'm not afraid to use it, so let's get down to business. So after everything has been unscrewed, we can see two boards, but in reality, only one is of interest to us. This board right here only contains the LCD screen, the speaker and the buttons. The other board is where all the magic is happening. So here we can see two memory chips, the top being the RAM and the bottom being the video RAM. And here we can see a bigger chip that says CPU, but it's actually a system on a chip that contains the actual CPU, plus a number of other components that we are going to explore in more detail later on. So let's start with the CPU. The Game Boy comes with a sharp LR35902 running at around 4 MHz. Now this is not entirely true in the case of the Game Boy and I will explain why later. This is actually an 8-bit processor and is actually a hybrid between Intel's 8080 and Zilog's Z80. The LR35902 took all the useful features of both these processors and stripped out everything that was not necessary. Now those of you who are more familiar with electronics will certainly know these two processors, as they were very popular back in the day. One thing that you may not know is that the 8080 was launched in 1974 and Z80 was launched in 1976. The Game Boy, on the other hand, was launched in 1989, so you can safely guess that the CPU was kinda old-fashioned. However, it managed to do the trick. So like I said, the LR35902 is an 8-bit processor, which means that most of its registers are 8-bit long. For those of you who are unfamiliar, a register is a very small but very fast memory which resides within the CPU. The CPU uses the registers in order to make calculations, load and store data. In the case of the Game Boy, the existing registers are namely A to F, H, L, SP and PC. Out of these registers, A to F, H and L are 8-bit long and SP and PC are 16-bit long. However, BC, DE and HL can be used in pairs in order to create 16-bit values. Register A is called the accumulator and is a special purpose register, so if you want, for example, to make an addition or subtraction, you will need to use register A. Register F is also special and it's called the flag register. So if you, for example, make a calculation and the result is 0, the Z bit of the flags register will turn 1, otherwise it will turn 0. So by reading this bit, you can find out whether the result was 0 or not. The end bit is called the subtraction bit. If the CPU is performing a subtraction, this bit will be set to 1, otherwise it will be set to 0. There are also some other flags here, namely the carry and the half carry flags, but we will not get into much more detail here. Now the 16-bit registers are used to access the Game Boy RAM. The SP register is the stack pointer and points to a special area in memory called stack. This area is used to temporarily store data when you, for example, enter a subroutine and restore them once you return from it. The stack pointer always points to the top value of the stack. If you push a value into the stack pointer will point to the new top value. On the other hand, if you pop a value from the stack pointer will now point to the second value, which is now the top value. The PC register is the program counter and tells the CPU the address of the next instruction to be executed. What is an instruction? Well, an instruction is a command that tells the CPU what to do. Every processor has a number of commands that it supports called the instruction set. In the case of the Game Boy, the LR35902 supports instructions for loading values to the registers, for arithmetic and logic operations, for CPU control, for bit manipulation, and for calling and returning from subroutines. Some of these instructions have been inherited from the 8080 and Z80 processors, but there are also instructions that are only present in the Game Boy CPU. Now at the end of the day, all these instructions are translated into ones and zeros in order to be understood by the device. The names are only symbols that are used so that humans can distinguish the commands easier. I mean, it's easier to understand what an LDR command is doing than having to remember all the ones and zeros that create this command. All the available instructions create a programming language called assembly. Now, assembly is different from many programming languages you may have used, like C, C++, Java or Python. All these languages do not force you to deal with registers and specific memory locations. Everything is done by the language and the compiler that translates the code to ones and zeros. On the other hand, in assembly, you have to specify everything by hand. Nothing is taken for granted. Let me show you what I mean. This is a piece of Python code that prints hello world to the screen. I mean, it's pretty straightforward. Now let's see the same program in assembly. Not as straightforward as you thought, right? Well, imagine having to write a whole game in this language. It would be such a pain. And assembly has another drawback. It is not portable. That means that if you write a program for a CPU and try to run it on another system with another CPU, it will most likely not work. So we should say a big thank you to all the developers who spent so many hours creating all the games that we had so much fun playing with. Okay, I think we've had enough of the CPU. Now let's take a look at the Game Boy memory. Now, as I said earlier, the registers dealing with memory, namely the stack pointer and the program counter, are 16-bit long, compared to the other registers that are only 8-bit long. Now, why is that? Well, that's because the Game Boy has a 16-bit memory address space. So how much memory can the Game Boy handle? To answer that, let's check out what the memory looks like. So the memory is like a two-dimensional array, and each line represents an address. The number of columns represent the number of bits for each address. In the Game Boy memory, each address contains 8 bits, hence the 8 columns. But how many lines are there? So since the Game Boy has a 16-bit memory address space, it can map up to 2 to the power of 16 addresses. But wait, we are used to calculate the memory in kilobytes, megabytes, gigabytes, and so on. How much memory is 2 to the power of 16? Let's get to our good old math to find the answer. So each line has 8 bits. In computers, 8 bits equal to 1 byte. So each line contains 1 byte and the total memory is equal to 2 to the power of 16 bytes. With some basic mathematics, we can say that 2 to the power of 16 equals 2 to the power of 6 times 2 to the power of 10. That is 64 times 2 to the power of 10. Now 2 to the power of 10 equals 1024 or 1 kilo. Similarly, 2 to the power of 20 equals 1 mega and 2 to the power of 30 equals 1 giga. Therefore, the total memory equals 64 kilobytes. Perfect, so we can use 64 kilobytes of RAM, right? Well, not really. In fact, we can only use 8 out of the 64 kilobytes of RAM. The rest of the memory is used for something called memory mapping. Let me explain what I mean by that. Most, if not all, of the components of the Game Boy have a number of registers inside them. If we want to use a specific component, we must have access to these registers. Otherwise, there is no way of communicating with it. But how can these registers be accessed? A good way to do it is to map all these registers onto the memory. If we need to access, for example, a sound controller, we just need to know where its dedicated registers are mapped onto the memory and just access them. As you can understand, the memory is divided into a number of regions, each of which is dedicated to a different piece of hardware. So, depending on your needs, you have to write or read a register of a specific memory region. This is called memory mapping. Mapping hardware onto memory in order to make it easier for you to communicate with it. Now, as you can see, the ROM takes up 32 kilobytes, which is half the memory. The ROM is actually the memory inside the cartridge where the game is stored. So once you plug the cartridge into the Game Boy, the ROM is mapped onto the beginning of the Game Boy memory. Now you might be wondering, are 32 kilobytes enough for every game? The answer of course is no. Some cartridges require more memory. In order to deal with this problem, the Game Boy divides the cartridge ROM memory into 16 kilobyte ROM banks. So say that the size of a game is 128 kilobytes. It will be broken down to 8 banks of 16 kilobyte each. So 2 banks can be mapped onto their own memory at the same time. Now the first bank that is placed to the beginning of the memory is always the same and is ROM bank 0. This never changes. The second bank can be either one of the other 7 banks, whichever is needed at that point. The correct bank is selected by a small chip inside the cartridge called Memory Bank Controller or MBC. Now one particularly interesting area in ROM is a little section at the beginning of the memory. This is called the boot ROM and contains the bootstrap code that does this. So the bootstrap code is located at address 0 in memory. When the Game Boy powers up, the program counter register is loaded with the value 0, so the CPU starts executing the bootstrap code. Now you might be thinking, okay, the Nintendo logo slides down, the sound is played, nothing fancy about that. However, there is much more to it. The bootstrap code serves both as a copyright and trademark security mechanism. Every cartridge has a copy of the bootstrap code in its ROM, otherwise the game will just not load. This was a way for Nintendo to control the games that were released for the Game Boy. Pretty clever idea if you ask me. Another thing the bootstrap code does is check the header of the cartridge in order to make sure that it operates correctly. After the above actions have been executed, the boot ROM is automatically disabled and will not be enabled again until the next power-up. Then the game boots and the CPU starts reading commands inside the cartridge. Now one last thing I would like to mention regarding the memory is that it operates at around 1 MHz. Now why is that important? Remember when I mentioned that the CPU runs at around 4 MHz but does not really run at 4 MHz? This is because of the memory. While the CPU's frequency is actually 4 MHz, it can only run at around 1 MHz because this is the frequency in which the memory can bring the necessary data. That means that the CPU has to wait for the memory to deliver its contents before doing any operations that require them. This issue is called memory bottleneck. Modern systems use cache memory in order to deal with this issue, but in the case of the Game Boy, no cache was implemented. Okay, enough with the memory, let's jump to another topic, which is the interrupt handling. Now, if you are not familiar with what interrupts are, let me give you an example. So imagine you are at home watching TV. At some point the doorbell rings, so you have to stop what you're doing and go see who's at the door. After you are done with that, you go back to your living room to watch some more TV. That's basically the deal with the Game Boy as well. The CPU is busy doing something. At some point an interrupt occurs, so the CPU has to stop what it's doing and jump to another location in memory, where the code that handles the interrupt is located. When the interrupt is handled, the CPU goes back to what it was doing before the interrupt occurred. Now there is a number of different sources that can trigger an interrupt, and depending on the source, the CPU jumps to a different location in memory to handle the interrupt. So say you are playing a Mario game and you press the right arrow on your D-pad. The joypad interrupt will be triggered and the CPU will immediately detect it. Then, it will stop what it's doing and it will jump to the memory location where the joypad interrupt handler is located. This code will tell the CPU that since the right arrow was pressed, Mario needs to move to the right. The same happens if any other button is pressed. Other types of interrupts are handled in a similar way. Speaking of buttons, let's take a look at how the joypad works. So the Game Boy has 8 buttons: A, B, Start and Select, and the 4 D-pad directions. Now, in order for the device to detect when a button was pressed or released, it uses something called General Purpose Input-Output, or GPIO. GPIOs are digital signal pins, which act as an input, an output, or both. In the case of the buttons, GPIOs act as inputs since the user is sending information to the Game Boy by pressing or releasing a button. Now, when a button is pressed, the corresponding GPIO will get the signal and it will propagate it inside the system. As we said earlier, this will cause an interrupt and the CPU will have to deal with it. Now, since there are 8 buttons, we should use 8 GPIOs, right? Well, that's one way to do it, but there is also a more efficient way. If you organize the buttons into a matrix of 4 rows and 2 columns, and you assign 1 GPIO for each row and 1 GPIO for each column, then you only need 6 GPIOs in order to detect which button was pressed. A simple idea that would save you logic and chip area. Now let's check out real quick how the serial data transfer works. As you know, 2 Game Boys can be connected together using the link cable. Now the link cable has only 3 wires. 1 wire for data in one direction, 1 wire of data in the other direction, and 1 clock wire. The clock is a digital signal that is used to determine when the data will be transferred. The 2 devices have to decide the master, which will be sending the clock, and the slave, which will be receiving the clock. The frequency of the clock is 8 kHz. As soon as the transfer starts, both Game Boys start sending data at the same time. 1 byte is being transferred at a time, and when the transfer is finished, a serial interrupt is being generated and the CPU will have to deal with it. Not anything else to talk about regarding the serial data transfer, so let's jump to the Game Boy timer. Now the timer is a component that, as its name denotes, counts from a specific value up to the maximum value, which is FF in hexadecimal or 8 ones in binary. When its value gets bigger than the maximum value, a timer interrupt will occur and the CPU once again has to handle it. The programmer can set the starting value, which the counter will use to start counting from, and the programmer can also decide how slow or fast the timer will count compared to the CPU clock. Now, why is the timer necessary? Well, you can use the timer whenever you are waiting for something to happen. If it does not happen after a specific amount of time, then you can use the timer to generate an interrupt and tell the CPU, well, I was waiting for something that it did not occur, so here is what you have to do to deal with it. Of course, there are many other uses, but this is just an example for you to understand the usage of the timer. So that's all there is for the timer. Now let's have a look at the sound controller. So the Game Boy has 4 sound channels, 2 square waves, a programmable wavetable, and a noise generator. Each channel has 5 registers for control, frequency, volume, length, and sweep. So from the control register, you can turn each channel on and off. you can also turn it off after some time that you can specify in the length register. From the frequency register you can control the pitch. As you can see, channels square A, square B and wave contain frequency bits inside the control registers as well, in order to give users more flexibility with the sounds they want to create. The volume register controls the volume of the channels, but it also contains something called volume envelope, which helps fading notes and sound effects in order to emulate standard instruments. The square 1 channel has also a sweeper register that is mostly meant for sound effects. Finally, the frequency register of the noise channel is meant to create noise by generating pseudo-random numbers. Apart from these registers, there are also other registers from which you can control the volume of the left and the right channel, and whether the audio will be transferred to the left channel, the right channel, or both.
Looks pretty complicated, so I can only imagine how many hours the programmers spent trying to create the soundtracks of the games. One last thing before we move on is that, although the Game Boy has a mono speaker, the audio jack outputs stereo audio, so if you plug in your headphones, you will have a much better experience. Now last but certainly not least is the Pixel Processing Unit, or PPU.
The PPU is responsible for creating graphics and displaying them to the screen. The screen itself is 160 to 144 pixels wide. It supports 4 shades of grey, which are actually 4 shades of green, and everything in the screen is 8x8 tile-based. Now what does that mean? Let's check out the game. The screen is divided into small squares which are called tiles. In total, there are 20x18 tiles on the screen. As you can see, there are repeating patterns and everything is aligned to a certain grid. Now let's get a closer look at what a single tile looks like. A tile consists of 8x8 pixels and can take one of the 4 shades of grey, like everything else. Therefore, 2 bits are needed in order to select the color of each pixel. So every tile row needs 16 bits or 2 bytes, and all the tiles on the screen need 128 bits or 16 bytes. In total, there can be up to 256 tiles in a game, and they are stored in video RAM or VRAM, which is an 8 KB memory. Now remember when I said earlier that there are 20x18 tiles on the screen? Well, that's the truth, but not the whole truth, because in video RAM there are 32x32 tiles, and what we see on the screen is just a portion of the picture. So in some games you might see that the image scrolls at any direction. But what about games that scroll infinitely, like Mario games? Well, in this case, the viewport moves from left to right and then it wraps around and starts from the beginning. Now, if you manage to update the tiles before the viewpoint reaches them, you can basically create an infinite world. Okay, one more thing that is common on the screen are the sprites. Sprites are objects on the screen that are not motionless and sometimes are bigger than the 8x8 pixels of a tile, so more than one tiles are needed in order to draw them on the screen. Examples of sprites are Mario and its enemies in Mario games. So why don't we get a closer look at the sprite? Every sprite, or object as Nintendo calls them, has some attributes. In fact, these attributes are stored in an Object Attribute Map or OAM, which contains information about the tile's number, where it should be displayed on screen, if it is flipped or not, its palette, and how it is drawn in comparison with a background. All these OAM entries are stored in a special kind of RAM called the OAM RAM, which is not a part of the video RAM. Now there can be up to 40 sprites on screen at the same time, but only 10 sprites per pixel line. If you draw, say, 11 sprites, the 11th one will be trimmed. Sprite tiles are also stored in video RAM just like background tiles. Now let's stop right here and think about something. There are 4 kilobytes of sprite tiles, 4 kilobytes of background tiles, 1 kilobyte of background map and 1 kilobyte of window map. But we only have 8 kilobytes of video RAM, so how are we going to fit everything? One way to deal with it is by having the sprite tiles and background tiles overlap each other. That means that some memory locations will be shared between the tiles, and we have to explicitly define which tile we want to use each time.
So final thoughts. As you can see guys, the Game Boy is quite a complicated device in terms of hardware. However, all the other handheld devices on the market at that point were not any simpler. Game Boy managed to take over the world not because of its cutting-edge hardware, but because it was cheaper, smaller, and it had better battery life compared to its rivals. So at the end of the day, Nintendo proved that it's not about the hardware, but about how you use it. So that's it for this video guys. Of course, this was by no means a complete description of the device, since I tried to strip out some too technical aspects. If you'd like to find out more information about how the Game Boy works, there are many guides out on the internet that can help you out. Of course, if you have any questions or remarks, please let me know down in the comments, and if you like this video, please hit the like and subscribe buttons. Thank you all, and I'll see you in the next video.